Hello everyone. Kotongwane, the native Claudia. Right, today we'll be looking at the module on engineering science entry called forces. Right, it's module 3 on your textbooks. Right, now under forces we look at coplanar and concurrent forces. Right, now before we get into what coplanar forces are and what concurrent forces are and what coplanar concurrent forces are, I want us to look at from which perspective we are able to look at these forces. It is very important that you understand the perspective in which we consider these forces, right? And that perspective is in terms of the planes that the forces will be acting on, right? Now I've drawn 3 planes on this diagram, right? You have this plane, right? You have this plane, and then you have this plane, right? So you have 3 planes that I've shown on this diagram, right? Now each of the planes is 2-dimensional, right? Each plane is 2-dimensional. Now if we consider this plane in particular, right, it is composed of 2 axes, right? 2 sets of axes, that's the x-axis and the y-axis, right? But we also have, or we're also able to look at forces from the perspective of this set of axes as well, the z-axis, right? Now at this level, we only consider, in fact, for nature engineering in general, right, we only consider forces acting on the xy plane, which is this plane, right? So because this plane is composed of the x-axis as well as the y-axis, right, we call it the xy plane or the yx plane, right? So meaningly, looking at this plane, this plane would be the zy plane, right? And then this one will be the xz plane, right? But like I said, for nature engineering, we only consider the xy plane, right? Because we only consider forces that are parallel with the y-axis or parallel with the x-axis, right? Or we consider forces that we are able to see from the perspective of this plane, right? Now let's dive deeper into the xy plane, right, and how we consider forces acting on the xy plane, right? Now I've drawn the xy plane here. Now as you can see here, right, each of the planes has essentially 2 sets of axes. By 2 sets of axes, I mean, if you look at the x-axis, right, the x-axis is a set on its own. Why? Because there's a side of the x-axis that is positive and one that is negative. Similarly, when we look at the y-axis, right, we consider that a set as well because there's the side of the y-axis that is positive and one that is negative, right? Now the side of the x-axis that is positive we also consider as the east side in terms of direction, right? And then the one that is negative we consider as west. And then with the y-axis, the positive y-axis we consider as north, and the negative y-axis we consider as south in terms of direction, right? What you can also see on this diagram or in this Cartesian plane is that a plane is not only composed of the x and y set of axes, right, but it is also composed of quadrants, right? So here you have the first quadrant, right? The forces acting here in this quadrant are said to be acting north of east or east of north, right? Then you get the second quadrant. Any force or any vector acting in this quadrant is considered to be acting in a direction northwest or west of north. Then you have the third quadrant, which is this one. The third quadrant also consists of 2 directions, right? So any vector that is acting in any direction in this quadrant is said to be west of south or south of west, right? And then you have the fourth quadrant. The fourth quadrant has east and south. So any vector acting anywhere in this fourth quadrant is said to be acting in a direction either east of south or south of east, right? Now, in considering forces, remember I said it is very important that we understand the perspective in which we look at those forces, right? And for this module, in considering forces, we will be applying conditions of equilibrium, right? Now remember, conditions of equilibrium, which we looked at when we were discussing Newton's laws of motion for the first module, motion, power, and energy, right? But just as a reminder, one of the conditions of equilibrium is sum of forces in the x direction is equal to, let's just say 0. Sum of forces in the y direction is equal to 0, right? Now, these conditions of equilibrium essentially mean that if the system of forces that you're looking at is in equilibrium, right, then we use these conditions to prove that the system of forces are indeed in equilibrium, right? And the way we prove that is by saying the sum of forces in the x direction is equal to 0, and the sum of forces in the y direction is also equal to 0, right? That's just one of the scenarios we are going to look at for this module, right? Another scenario would be looking at forces that are acting on a system, and you are not told whether or not the forces are in equilibrium, right? So again, you use conditions of equilibrium, right? But now they won't be equal to 0. We have no idea what they'll be equal to, right? In this scenario, because you haven't been told if the forces are in equilibrium or not, right? This is how you apply conditions of equilibrium, right? By not saying they're equal to 0, because essentially either they are not equal to 0 or we don't know if they're equal to 0, right? Either way, we still need to apply conditions of equilibrium, right, to calculate the vector sum of forces, which is the resultant. Right, now if the vector sum of forces, the resultant of the forces acting on the system, if it is not equal to 0, then it means the system of forces are not in equilibrium. Right, when the system of forces are in equilibrium, it means the resultant of vector sum of forces is equal to 0. Right, now I bring up conditions of equilibrium because it is important that you understand that in applying conditions of equilibrium, regardless of the scenario, right, the forces you are going to use, right, for sum of forces in the x direction must be forces that are parallel with the x-axis. Hence the term sum of forces in the x direction. And then the sum of forces in the y direction, you are only able to use forces here that are parallel with the y-axis, right? Forces like this one, right? This force is parallel with the y-axis. This force is parallel with the x-axis, right? But those aren't the only forces that we get to consider, right, acting on this plane, right? We also get oblique forces, right? Oblique forces are forces that form an angle with the Cartesian plane, right? So for instance, this one is forming an angle of theta. This angle of theta is measured from the x-axis, right, to the oblique force. Or we can say that the oblique force, call this beta, right, is at an angle of beta from the y-axis, right? We are also able to consider these forces, but we cannot use these forces exactly as they are, right, in applying conditions of equilibrium. Why? Because oblique forces are not parallel to the y-axis nor parallel to the x-axis, right? So what we do, right, with oblique forces instead is we resolve them into their components, right? We resolve them into the components. So you'd have the vertical component, or the component of the oblique force in the y direction, as well as the horizontal component, or the component of the oblique force in the x direction. Now the components we are able to use in applying conditions of equilibrium. Why? Because the components, right, for instance, the vertical component is parallel with the y-axis, so you are able to consider it here. And then the horizontal component is parallel with the x-axis, hence you are able to consider it when applying conditions of equilibrium for the forces acting in the x direction. All right. Now, in terms of how you resolve an oblique force into its components, right? It's pretty straightforward, right? This represents the oblique force, right? The components of this oblique force must be such that they are acting in a direction that is towards the direction of the oblique force, right? So for instance here, right, for instance, we want to resolve this into its components, right? And in resolving this into its components, we must make sure that its components is headed in a direction that is following this one, right? So in order to do that, right, if you consider the vertical component, right, for the vertical component to follow this direction, it has to be acting upward, right? Meaningly, we cannot say that the vertical component of this is acting downwards, right? This direction is headed away from the direction of the oblique force, meaning it is incorrect. So for this to be correct, right, it has to be headed in a direction that is towards the direction of your oblique force. But similarly with the horizontal component, right, for us to correctly determine the horizontal component, right, as well as its direction, it must be headed in a direction that is towards the direction of the oblique force, right? Meaningly, right, we can't say that this component is headed in that direction. Why? Because now this direction is headed in a direction that is away from this, right, which is obviously wrong. Therefore, it means this is the correct one. All right, so the components of this oblique force will be this one and that one. Similarly, if say now we are in this quadrant, right, you have a force that's headed in that quadrant. You have to resolve this into its components, right? Bearing in mind that the components of this oblique force must be headed in a direction that is towards the original direction of this oblique force, right? So you have the horizontal components and you have the vertical component and you have the horizontal component, right? For the two to be headed in the same direction or towards the direction of the oblique force, it means this must be headed in that direction and then the horizontal component in that direction, right? And then third quadrant, right? So forces that are anywhere in this quadrant heading in that direction, right? Those ones have to be heading in this direction. So the horizontal component headed in that direction, vertical component in that direction. This way, the two components, right, are headed in a direction that is towards this one of the original vector, right? And then you get vectors that will be in the in the fourth quadrant, right, headed in that direction. Right, so those ones, right, in resolving it into its components are going to be headed in these directions. The horizontal component will be headed in that direction. The vertical component will be headed in this direction. Right, that way the two components are heading in a direction that is towards this one. Right, you obviously cannot have, right, like I've just explained, you obviously cannot have this, right, or this, because either way, right, if you're saying this is the case, right, then you're saying essentially the vertical component of this oblique force is headed in a direction that is away from this direction, which is incorrect. Right, the correct one is this here. Right, so that's the simplest way of representing the components of an oblique force, right, in terms of direction. Right, that is how you look at it. Right, so that's number one. Number two, now each of these components are going to be in terms of a ratio, right, be it cos or sine. Right, now I prefer using the angle, so the trig ratio that each of these components is going to be in terms of will be based on which angle you are going to use to represent the two components. Right, by which angle I mean if you used the angle that is referenced on the x-axis, or you use the angle that is referenced from the y-axis. Right, now if you use the angle that is referenced from the x-axis, right, let's call this oblique vector A. Right, doesn't matter the magnitude, right, so let's just call it vector A, or oblique force A. Right, its magnitude, let's just refer to it as A. Right, now you have to resolve it into its components. The vertical component, so let's say the A in the y direction, so the vertical component of A is headed upward. Because it's headed upward, you take it as being positive. Right, the oblique vector is A. Now if the angle you are using is a reference from the x-axis, then this will be in terms of sine theta. Right, and then the horizontal component of A, so A in the x direction, will be equal to, you look at the direction of your vector, it is headed towards the positive x direction, so this remains positive. Right, the vector is A, and then you use cos theta. Right, if the angle you are using is a reference from the x-axis, then the x component will be in terms of cos, and the y component will be in terms of sine. Right, whereas if the angle you are using is a reference from the y-axis, so for instance beta here, right, is a reference from the y-axis, so from the y-axis to the oblique vector A, we have this angle beta. Right, if you use beta instead, that will mean the y component of A will be A cos beta, and the x component will be A sine beta. Right, so how you express the component of an oblique force depends on the angle that you are using. If the angle you are using is a reference from the x-axis, then the x component will be in terms of cos, and the y component will be in terms of sine. Whereas if the angle you are using is a reference from the y-axis, then the y component will be now in terms of cos, and the x component will be in terms of sine. right? So if I were to suggest here, I would say that rather stick with referencing your angles from the x-axis. Right, so however many oblique forces you have, right, on your system, right, if you have to resolve it into its components, so when using the analytical method, which is we are going to get to just now, right, but if you have to resolve the oblique force into its components, or the oblique vector into its components, right, use the angle that is referenced from the x-axis, so that all your x components will be in terms of cos and all your y components will be in terms of sine. Right, that way when applying this condition of equilibrium, all your x components, right, all your x components of your oblique vectors will be in terms of cos, right, so you will not have any component here that is expressed in terms of sine. Why? Because all your vectors or all your oblique forces, right, the angle thereof, you have used the one that is referenced from the x-axis, right? Similarly with applying this condition of equilibrium, so forces, sum of forces in the y direction, you are only going to consider forces here that are in terms of sine. Right, but again, in order for that to happen, you must reference all the angles you are going to use from the x-axis. Right? Now, the reason why I say if you are going to have to resolve an oblique force, right, for problems based on forces, right, there are essentially a couple of methods that we are able to use, but the methods are grouped into two groups, right? The one group, right, of applying conditions of equilibrium is based on the analytical method. Right, the analytical method is the mathematical method where you actually calculate what you are looking for. Right? With this method, this is the one we'll be using frequently at this level. Right? The graphical method, you will use more in strength of materials in N5. Right? Also in mechanotechniques N6, you will get to use it. Right? More especially for mechanotechniques N6, right, you will use the graphical method, right, but just in general, right, you have the analytical method and then you have the graphical method, right. Now with the analytical method, right, that is where we apply conditions of equilibrium like so, right. That is where we apply conditions of equilibrium mathematically, right, and then obviously in this case you'd have to resolve your oblique vectors into components, right, making sure that to avoid any confusion you reference your angle, or you use the angle that is referenced from the x-axis. That way your x components of your oblique vectors will be in terms of cos, and your y components of your oblique vectors will be in terms of sine. Alright, so with the analytical method, we apply conditions of equilibrium, right? Depending on the scenario, if the scenario is that you have a system of forces acting on the system and those forces are in equilibrium, right, how we apply conditions of equilibrium is by saying the sum of forces in the x direction is equal to 0, right, in that scenario. So this would be equal to 0, and the sum of forces in the y direction also equal to 0. All right. And then you get a scenario where you are given a system of forces and they do not mention whether the system of forces are in equilibrium or not. Right. So you'd again still apply conditions of equilibrium, right, but not equating them to 0. Right. So here you say the sum of forces in the x direction, then you add up all the forces in the x direction, right, and you get whatever answer here. Similarly, with the sum of forces in the y direction, you add the forces that are parallel with the y-axis. Right, now in that scenario, right, after having calculated the sum of forces in the x direction and sum of forces in the y direction, you then have to calculate the resultant force. Right, the resultant force is the vector sum of forces acting on a system. Right, essentially, when applying conditions of equilibrium, right, this here we are able to take as, in fact, you can take, or is in fact, the x component of the resultant force, and this here essentially represents the y component of the resultant force. That is why after having attained, or after having determined the two components, in calculating the resultant, you simply use Pythagoras. Right, you use Pythagoras theorem, right, to determine the magnitude of the resultant. Right, so this is the x component of the resultant, and this is the y component of the resultant essentially. And this gives you the resultant of the magnitude of the resultant. Right, now in calculating the magnitude of the two components, right, we have to consider direction as well, because remember, forces are vectors, and with vectors we consider direction. Right, now that is to say that when calculating the magnitude of the x components of the resultant, if the answer you get is negative, right, remember, going back to your plane, if the answer you get for your x component is negative, that means that the x component is headed west, which is towards the negative x direction. Right, so if you get this as negative, right, you have to express your answers as west. Remember, the sign tells us the direction. So meaningly, if it is positive, right, if it is positive, the positive x direction is east. Right, so if you get this as positive, all that means is that this is headed east. Right, similarly with the y component, if you get a positive answer, right, it means the component is headed towards the positive y direction, which is north. And then if it is negative, it means it is headed towards the negative y direction, which is south. Right, and it is very important that you indicate the direction. So for instance, if the x component is positive, it means it is headed east, and if the y component is negative, that means it is headed south. Right, and it is important to indicate these directions. Right, it is important to indicate these directions. Why? Because these directions allude to the quadrant in which your resultant is acting. Right, so having calculated the two components, by the time you calculate the resultant force, you will already have an idea as to the quadrant this resultant force is acting, right, based on this here. So if the x component is east and the y component is south, right? The quadrant where you have east and south is the fourth quadrant, meaning that your resultant force is acting somewhere in this quadrant, right? Now, to get the exact point where it is acting, you then have to calculate the angle that it is making, right? Either from the x-axis or the y-axis. Right? So if in this scenario that's the x component is headed east and the y component is headed south, right? This is essentially what you will get. Right, you have the x component headed east and you have the y component headed south. Right, if that's the case, that means the resultant is acting somewhere in this direction. Right, remember at this point you already have the direction of the x component and the direction of the y component, which tells you of the quadrant that the resultant is acting. Right, like I said, east and south is in this quadrant, meaning that the resultant is headed in this direction, right? Anywhere here but in this direction. Therefore, when drawing this vector diagram of the resultant force, right, you make sure that this is headed east. So the two components, you must make sure that you draw them, right, following a head to tail direction. Right, and then the resultant will be in a direction that opposes head to tail. Right, I'll explain the head to tail matter later when we look at the triangle law. Right, and then in calculating or to pinpoint the exact point where the resultant is acting, right, you have to calculate the angle. Right, now if the angle you are going to calculate is a reference from the x-axis, right, as you can see here, I have two angles. One is a reference from the x-axis, the other one is a reference from the y-axis. Right, when using this angle, right, remember these trig ratios. So these trig ratios we're able to use if the triangle we are using is a right angled triangle. Right, so to get this angle or any one of these angles, right, we use tan theta, and based on this, tan theta is equal to the side opposite. The O stands for opposite, so the side that is opposite the angle you want to calculate divided by the side that is adjacent to the angle. So tan theta is equal to the side that's opposite the angle. There's your angle. The side opposite the angle is sum of forces in the y direction, divided by the side that is adjacent to the angle. So divided by the side that is adjacent to the angle, which is sum of forces in the x direction. Right, so that is to say, when calculating an angle that is referenced from the x-axis, this is what you use. All right, so here for this scenario, for instance, right, the resultant you would then say is equal to whatever magnitude you get. Now, how you express the direction, right? Each of the quadrants has two directions, right? If your resultant or if your force is not acting parallel to any of the axes, it means it will be acting in a certain quadrant, and each quadrant has two directions, right? This one in particular for this scenario, right, is the fourth quadrant, and it has two directions, east and south. In expressing the direction, right, so remember at this point you've already written the magnitude. In expressing the direction, right, in expressing the direction of the resultant or of your force or your vector, the first direction you write here is based on where this angle is referenced from. Right? Remember we said theta is referenced from the x-axis. The x-axis here, as per the x component, is headed east. So here you first write east. The angle itself, the second direction pinpoints, right, the quadrant. Right, so the second direction pinpointing the quadrant will be south. Because like I said, at this point we've already established that the resultant is in which quadrant. And for this scenario in particular, it is in the fourth quadrant, which has these two directions. The first and last direction will be determined by which angle you are using. So if you're using the angle that is referenced from the x-axis, right, you look at the direction of your x component. The x component is headed east, right, and you write the first direction here. The first direction essentially tells us where this angle is referenced from. And theta is referenced from the x-axis. X-axis, or the direction of the x component, is east. That is why we have east here first, because this angle is referenced from east. And then the second direction pinpoints essentially the quadrant. Right, so because the quadrant is the fourth quadrant, obviously this has to be south. Right, even aside from that, you look at the direction of your other components. Right, so the first direction was referenced from this. Your other component is this one, so you look at the direction of this component, which is south, hence you have south here. So there's a number of ways in which you can look at this. Right. Now, if the angle you calculated is this one instead, so the angle that is referenced from the y-axis, right? So beta is referenced from the y-axis. So again, you use the very same trig ratio, tan beta, right? Tan beta is equal to the side that's opposite the angle, which is this one. Hence you have the sum of fx here, divided by the side that is adjacent to the angle, which is this one, right? That is how this formula comes about. So tan beta, or having to calculate the angle that is referenced from the y-axis, you say tan that angle is equal to the x component divided by the y component, essentially, which is vice versa of this. And then in stating your resultant, right, you write down the magnitude of your resultant, and then in terms of direction, again, the first direction tells us where this angle is referenced from, and beta is referenced from the y-axis, and the y-axis or the y component is headed south, hence we have south here, the angle itself, and then the second direction pinpoints the quadrant. So seeing that the angle is referenced from the y component, it means the second direction will be east. Right, and that is how you express direction. Right, again with this one, right, just like how we resolve oblique forces into its components, remember here I showed you how we would express the components depending on the angle that we use, right? And I expressed that it is much better if we stick with using the angle that is referenced from the x-axis, so that all the x components will be in terms of cos and all the y components will be in terms of sine. Right, similarly with this one, right, not to get confused as to which formula to use or how to express tan theta or tan beta, right? Stick with using tan angle is equal to y component over x component, right? This way we know that if we are using this formula, we know that whatever angle we have here is referenced from the x-axis. Right, so that is the analytical method. Then we get, so the analytical method is the one that we'll be using predominantly. Right, it's the one we use predominantly for nature engineering, right? But we also have the graphical method. Right, with the graphical method, you have the first polygon, right? The first polygon where we use, in fact, for all the polygons, right? For the graphical method, we use what we know as pose notation, right? This we learned, I believe, in N1, right? We did it again under the parallelogram, right? We also used pose notation for that, or we revisited pose notation when we looked at the parallelogram in N2, right? That's the method we use in drawing a force polygon, right? Or a polygon of forces, right? What polygon of forces essentially means is forces that are essentially more than 3, because if they are less than 3, right, or if they are equal to 3, then you simply use the triangle of forces, right? So if your vectors form a shape, right, that takes more than 3 forces, then you refer to it as a polygon of forces, right? But if the shape of the vectors you are drawing forms a triangle, then we call it a triangle of forces, right? Then we get a coupled polygon, right? A coupled polygon you will get to do in mechanotechniques under balancing, right? When you look at the concept of balancing or rotating bodies, right, that is when we'll discuss this coupled polygon, right? In engineering science N3 in particular, right, this is what we use, right? This, in fact, the concept of the triangle law, we are going to use, right, in determining members of a roof truss, right? So roof trusses is a unit we are going to come across in module 3, forces, right? And this is the concept we will use mainly there, right? So you have a triangle law or triangle of forces. Now these two are not necessarily the same thing, not necessarily, right? Because the triangle of forces we use for cases, also for both cases where the system of forces is in equilibrium, and for cases where the system of forces are not in equilibrium. Right, we'll discuss how that would look like graphically, right? But the term triangle means 3 forces acting in the system, right? So this, we're able to call the forces, if there are 3 forces in the system, we can use the triangle of forces. That is saying that what that essentially means is that you draw a polygon, right? You draw, or you use the graphical method to determine the magnitude and directions of the forces, or of the 3 forces to be, or in particular, right? Be it the forces are in equilibrium or not. Whereas this one, we are only able to call it the triangle law if the forces are in equilibrium, right? What the triangle law states is that if 3 coplanar concurrent forces act on a body, and keep the body in equilibrium, then the three forces drawn, right, this is very important, right, drawn head to tail, right, so this is the direction of the vectors, drawn head to tail can be represented in magnitude and direction by the sides of a triangle. Right, what that means is this here. Right, you have three forces acting on a body, and those three forces are keeping the body in equilibrium. Right, what that means is that, let's consider these three forces. Right, if one is going in this direction, and the other one is going in that direction, and the last one is going in that direction, head to tail essentially means that the direction of the vectors are essentially following each other, right? Following a head to tail direction, right? So head to tail direction, right? If all the vectors, right? If all your vectors on your polygon are such that they are following each other, right, in terms of direction, then what that tells us is that the system of forces is in equilibrium. Right? And then if the system of forces, right, if you have three forces but they are not in equilibrium, right, how we show that is by making sure that one of the forces is going in a direction that doesn't or opposes, that doesn't follow a head to tail direction or opposes the head to tail direction. So if you look here, this force and this force follow a head to tail direction, but this one, right, goes in a direction that opposes head to tail. Right, that means that these forces are not in equilibrium. Right, so the first scenario and second scenario are both triangular forces, but in terms of the triangle law, only the first scenario, so this scenario, only this scenario is the triangle law, because with the triangle law you have to have your forces must be coplanar, concurrent, and must be such that they are keeping the body in equilibrium. If that's the case, those three forces can be drawn in such a way that they represent a triangle, the direction of which must follow a head to tail direction. Right. Now, as far as equilibrant, right, we have discussed resultant. So remember we said resultant is the vector sum of forces acting on a system that we determine by applying conditions of equilibrium. Right, now the equilibrant is essentially a force that balances the system. Right, it's a force that balances the system of forces or the forces acting on a body. And the relationship between the equilibrant and resultant is that the equilibrant is the same in magnitude with the resultant force, but it is opposite in direction. Right, so that is to say, to calculate the equilibrant, right, you simply calculate the resultant or the vector sum of forces acting on the system, and the equilibrant, or to determine the equilibrant, the equilibrant will be the same in magnitude with the resultant, but opposite in direction. Right, now in this scenario, remember we said that the resultant was headed east, angle south. Right, so to determine the equilibrant, right, using this scenario, so if the resultant, for instance, is this, it means the equilibrant will be equal to same in magnitude with the resultant, but opposite in direction. So opposite of east is west. The angle remains the same. Opposite of south is north. Right? So if we were to show a schematic illustration of this, so let's say the red represents the resultant and the green represents the equilibrant. So if the equilibrant, if the resultant is acting somewhere here in that direction, that's the resultant, right? Opposite of this, right? Remember, this is east, south, right? Opposite of east, south is west, north, which is in this quadrant. Okay, let's do this, which is in this quadrant, and that's green. So that's headed in that direction. This is E, that's theta. So the angle remains the same, and that's theta. The angle remains the same for obvious reasons. If you look at the angle, if the equilibrant is the opposite of the resultant in terms of direction, right? Schematically, this is what it would look like. Hence, if you look at this angle, whatever this angle is, it will be equal to this angle. Vertically opposite angles. Right, so meaningly, if this is theta, it means that is theta. Right, so that is why the angle remains the same. Right, now I really hope you found this helpful. Right, so this is just the basics of forces. Right, I didn't speak of Newton's laws of motion because that I spoke about, we discussed when looking at module 1, motion, power and energy. Right, so this is in addition to that. Right, these are the key concepts we'll be using in determining whatever we need to determine, right, for coplanar and concurrent forces. Right, now coplanar and concurrent forces, right, coplanar essentially means forces acting on the same plane, right? That is why it is important to understand the perspective of forces, right? In applying conditions of equilibrium, we have to investigate in which plane the forces are acting, right? And the way we do that is based on which plane we are going to be using. Now, we are going to be using the XY plane, so we only consider forces that we can see from this perspective. Right, so those are forces that are parallel with the x-axis and parallel with the y-axis. Right, and then also forces that are oblique, that which we resolve into its components will be parallel with the y-axis and the x-axis. Right, so it doesn't matter where on the plane the forces are acting, as long as if you look at the forces from this perspective, you can see them, right? Then those forces are coplanar, acting on the same plane, right? And then you get concurrent forces, right? Concurrent forces are forces, for instance, if you consider this force, this force, this force, and this force, right? If you consider those four forces, right, aside from them being coplanar, they are concurrent as well. Why? Concurrent forces are forces that are acting on the same point at the same time. Right, so because the four forces are acting on the same point at the same time, it makes them concurrent. Right, so these are the concepts we've discussed are concepts that are going to help us in determining forces that are coplanar, forces that are concurrent, and forces that are coplanar concurrent. Right, so you're gonna get forces that are just coplanar, right? So acting on the same plane but not on the same point at the same time, right? Those cases will be on laminars the most. So laminars, as well as beams, levers, right? Those kind of scenarios. And then you get scenarios where the forces are coplanar as well as concurrent. So meaning acting on the same plane, on the same point, at the same time. Right, so we are going to, the concepts we discussed here, we are going to use in solving those kind of problems. Right, so stay tuned for more videos. If you liked or if you found this video helpful in particular, right, hit the like button. And then also subscribe to the channel so that you don't miss any further content. Right, we are going to be looking at a couple of scenarios on module 3. Right, once we're done in module 3, I will look at statics, so beams. Right, after which we'll then look at friction. Right, so you don't want to miss those. Right, after that, of course, we'll look at steam generation and then hydraulics. Right, steam generation is one of my favorite modules here. Right, hence the bit of singing there. And then hydraulics, I love hydraulics as well. Right, so that's if you wanna understand all of those modules in engineering science N3. All right, just subscribe to the channel and stay tuned. Hit the notification bell as well. All right. Yeah, all the best, man. Cheers.